All right, today we'll be talking about the quantum mechanical model of the atom. So before we do, we need to first review where we're at. And so what's happening in that emission spectra and what's the Bohr model? And so when we're looking at this, we're seeing that exactly what we saw in the lab. We take that tube containing hydrogen, we shine it through a prism, we split it open, and we have four very specific wavelengths of light in different intensities, right? We saw a really intense red, and then slowly less intense green, blue, and violet. And so what we said here was that electrons can move up and down from these orbits, okay, the circular paths around the nucleus. And so we said that, well, it can jump from that 2 to 3, 3 to 4, 2 to 4, 2 to 5, 2 to 6. And then when it wants to release that energy, it falls back down and shoots off energy at a very specific amount, which translates into a very specific wavelength. Okay? And so the difference between N2 and N3 was the red, and N2 and N4 was green. So anyway, in this idea, we said, well, light can act as a wave, right, because we have it releasing waves, or as a particle, because it is quite literally a particle, these electrons moving up and down. And so with that, then, what can we apply the other way? Can electrons then behave in that manner? Instead of just as particles, can they behave like waves? And that's the start of where we're at today. Because what we really see in the Bohr model is that as you move into these bigger elements, okay, when you move from hydrogen to helium to lithium to beryllium to boron, that suddenly it becomes less and less predictable and then doesn't apply at all. The Bohr model does a really good job at explaining hydrogen, and then basically from there on out doesn't do so great of a job. And so what we want to do now is, instead of just applying the idea of a particle to light, can we apply the idea of light, the waves, to the particle, electrons? And that kind of brings us to where we're at, which is these questions about the Bohr model. Can it really be that simple? Are these electrons locked into these circular orbits? And is there a better model? And when we start thinking about that concept of, well, if light can behave like a particle, not just a wave, then can a particle act like a wave and not just a particle? And that kind of brings us into this, into Erwin Schrödinger and his proposal for the model of the atom. And it's that, well, he thought that Bohr's was a bit of an oversimplification. He proposed that electron movement can be explained by a series of wave functions, okay? And the idea was that, well, electrons can behave like a wave, not just a particle. And so what is a wave function? So a wave function is fairly simple. It's just a mathematical equation, right? But specifically one that describes the quantum state of an electron. And so that would be a particle as a function of four things: momentum, time, position, and spin. Or where is it going, where is it at in time, and where is it at in space, the position, and then how's it spinning? Because electrons have a spin. They could spin, think about it like backwards, they could spin forwards, or think about it clockwise and counterclockwise. We know this because of magnetism. It's how magnetism works. And that's a conversation for another day. All right, so these wave functions describe four different things. Okay, now because electrons are so small, because their movement is influenced so easily, Heisenberg came up with his uncertainty principle. Another scientist, right? He came up with this concept that it's impossible to know exactly where an electron is and where it's moving, where its direction and speed. And so the idea is that if we look at its speed and where it's going, we influence its position. And if we look at its position, we influence its speed and where it's going, because these particles are so small. So in it, there's some uncertainty about electrons in general. And that's where this wave function comes in, because the main part of this wave function is it is a probability. It doesn't explain exactly where an electron is at a point in time, where it's going, any of those things necessarily. It instead describes where is the most likely location for us to find it, or where is the most likely location for it to be. And so the easiest way to kind of talk about this is by talking about baseball. So I want you to think about this, diagram right up here, where there's a batter at the plate hitting a ball. And so the concept of probability is that this might be the most likely path for a baseball to travel in order to hit a home run, right? Let's, kind of neglect all this, the angles and the height, but this is the most likely path. What we can agree on is that, the ball is going to go over the wall within a certain, you know, space here. Maybe not always just over the wall, maybe a little bit higher, all right? But nonetheless, this is the basic location. And the hit, well, the bat can be a little lower, a little higher, maybe hit a little further back, but it all starts very similar. The difference now becomes the path, because some balls are going to go higher and then go over the wall. Some balls will go lower, right? A more direct path over the wall, all right? But this is the most likely, the average path. So if we were to design an equation around this, a wave function, what it would be, or a probability, we would have this being the most likely. But then all around it, there'd be other lines where home runs were hit, okay? And some drastically less likely. Maybe somebody hit it sky high and over the wall, right? And that might be a less likely path. But there's a probability to it. Every single home run hit does not follow this path, but most of them are closer to this path than further. That's a probability. And so Schrodinger proposed it, instead of them traveling in these specific locked in orbits around the nucleus, they could instead be in this probability function. They're free to kind of travel how they want around the nucleus in any direction at any momentum, right? However, there is a most likely path, a most likely area to find them. And he called these things orbitals. Okay? Now, what we're really talking about is electron density, the probability that an electron will be in a certain region of space at any given time. And so if we were to zoom in to an atom, there would be a spot where we'd be most likely to find that electron, right? The same way that this is the path most likely for the ball to travel. That does not mean that that's where it's going to be every time, okay? At certain times of the day, you are most likely in chemistry class. But it doesn't mean you're always there. You could have gone to the bathroom, the nurse. You could be out sick that day, right? There are exceptions. Your most likely location, though, on certain days is in my room for chemistry, okay? And so that's the idea of these probability functions where there is still this area of high probability, high density. And we can see that with at least these types of orbitals, the s orbital, it's very similar looking to our Bohr model. All right. The problem is that the the orbitals do not all look this way. All right, those probability functions don't all come out in this nice circular pattern like orbits around the sun, all right, or like the Bohr model. As you go up in energy level, so when you go from that n equals 1 to n equals 2, there's now some extra sublevels. And that's what we're going to look at here. And we don't need to get any crazy understanding of these. We just want you to have a very basic, an image in your head here. So what happens is, as you go away from the nucleus, as you go from, let's see, from n equals 1 to n equals 2 to n equals 3 to n equals 4 to n equals 5, as you travel away from the nucleus, there are subshells to each energy level. So the n equals 1 only has one sublevel. N equals 2 has two sublevels. N equals 3 has three sublevels. And that's what we're going to see here is how they look. So in n equals 1, there's only one sublevel. It looks just like this. It's a nice sphere. But in n equals 2, they now introduce a second look. So there's a subshell that looks like that in S, but there's also these p orbitals, okay? And they look like dumbbells. Essentially, there's this on one side, this on the other, and there's a little nucleus inside there, and there's what's called a nodal plane. The electrons cannot go from one side to the other. They're kind of stuck, right? They can't cross. There's no probability that you're going to find them in that nodal plane, okay? And so what happens with the p subshell is there's not just one of them, there are three, because one's oriented in the x direction, one's oriented in the y direction, and one is in the z direction. And so you can have three subshells here. Now with the when you get to the third energy level, you introduce the d orbitals, and these things we call clovers. All right, and at this point, you're probably starting to get a little bit confused. So let's look at an energy diagram to show it. This is how it works. So we can see down here, we still have that familiar n equals 1, 2, 3, 4, 5, 6. There are these shells, right? The principal shells, or over here, kind of reminds you of the Bohr model, right? But within each of those principal shells, there are subshells, okay? In n equals 1, there's only one subshell. In n equals 2, there are two subshells. In n equals 3, there are three subshells. 4, there are four subshells. Now, in 5, there would be 5 subshells, but we haven't discovered any atoms yet, any elements yet that are that big that they would have 5 subshell, the fifth subshell. We haven't gotten that far. So that's where when you look at 5 and 6, it suddenly gets less. It's not that there are less. Theoretically, there are more. However, we can't say because we haven't discovered these things yet. Okay? So, as we go up each subshell, right, there are S's. Every single one has one of those. Then there are P's, but the first one doesn't have that subshell. Just the second, third, fourth, and from then on. Then in the third one, we introduce the D's. Then in the fourth one, we introduce the F's. And so as we go up principal shells, we add another sublevel, okay? And then each one of these corresponds to a shape. Again, S is spherical, P is those dumbbells, D is the clover. And we're going to really dive into this more right after this video when you really start talking about what are called electron configurations, where you explain how these electrons fit, where they go. All right. But for now, we just wanted you to get that kind of visual, understand that there are these things called subshells. And this is probably a nice diagram to understand it, that as you go out, because those orbitals become bigger, right? Those principal levels become bigger, we can add in more sublevels as we become further from that nucleus. And so again, that first one only has one, the second one has two, the S and the P, the third one has three, the S, the P, the D, the fourth one has all four, the S, the P, the D, and the F. Okay? And then each one of these subshells has more, more to it as you go up. So the S only has, one, then the P has three, the D has five, and it has to do just with the probability functions as they are around the nucleus. And that's what we're getting to here, which is that there is one S, then there are three P's, there are five D orbitals, and if we showed you the F orbitals, which are crazy looking, there are seven of those. Okay, but that's the concept here. So we're going to get into electron configurations after this, where we talk a little bit more about where they are around the nucleus. All right, and from this, guys, we'll gain more understanding. We're not expecting you to know everything there is to know about the quantum mechanical model after this video. We're just expecting you to have kind of a basic understanding. This whole idea of the atom is considerably more complicated than we originally thought.